This topic, before we talk about partial differential equations, I want to talk about this topic where you do change of variables for partial derivatives. Let's say f is a function of x and y, and therefore you can talk about partial derivative of f with respect to x and partial derivative of f with respect to y. Those make sense, right? And I assume that everyone knows how to do these partial derivatives. If I give you the explicit formula, those are not hard. What is hard and often a source of confusion is if you do change of variables. So suppose you have x equals to u and y equals to u plus v. So that means I'm doing a change of variables from x and y to u and v. Right? Now if that happens, I can ask the following question. Can you express the partial derivative of f with respect to x using u and v? And one could say, well, look at x, that's same as u, right? So you would think, oh, this must be same as this, right? So that would be your first guess, okay? How many of you know the correct answer? So my answer, I'm trying to say that this is wrong, okay? Yeah. It's shocking, isn't it? Right? Yeah. It's not right. Yeah. Does anyone know how to get the correct answer? Yeah. So I figured. See, it's something that you should have learned in multivariable calculus, but they don't teach you, so you end up with this gap in knowledge. So the answer is this is not right. So let me try to explain. The problem with partial differentiation is that it's assuming something extra that's not in the notation. So let's think about what this means. Partial derivative of f with respect to x, it really means it's the rate of change of f, right, with respect to x while fixing y. Right? You're treating y as a constant and you're trying to differentiate f as a function of x while holding y as a constant. That's nothing special, right? This is exactly how you learned it, right? You agree, right? This is exactly the definition you learned. Now, try to compare this with the other definition, the partial derivative with respect to u. It's exactly the same thing. It's the rate of change of f with respect to u. So what you're doing is you're changing u ever so slightly. You increase u ever so slightly. That's going to bring change in f, and then with that you take the ratio and see what the ratio is. That gives you the rate of change, right? But here's something that's not in this notation, which is while fixing what?
U plus V.
No. While fixing
V on.
V. Because at this level, when you have U and V, when you have U and U plus V, then you're representing F as a function of U and V. And in that sense, when you say partial derivative of F with respect to U, you end up saying that you're fixing V. Now, you might think that fixing V and fixing Y is the same thing, but it's not, right? Because, see, if you fix V and you change U, you see that both X and Y is changing. Right? Agreed? Okay. So, once you kind of see where the problem is, let me pose a question and let's try to actually answer it. Okay? So if you agree that they're really not the same thing, let me pose a question and we'll try to answer that. Okay. So, let's say this is given, and the question is find partial of F with respect to X, partial of F with respect to Y, and also partial of F with respect to X twice. In terms of U and V. Okay, so that's the question. And let's try to find the correct answer for this. Okay. And here's how we think. So what we want to do is you first let U as X, and then V would be, if you solve the second one by V, what would happen? V would be Y minus U, right? Oh no, it's just an Y is U plus V. Okay, well, I'll just write this just for completeness. But I'm not so sure which one I'm supposed to be using, okay? All right, so you can view this in two different ways. So one is you can view X and Y as a function of U and V. Okay, so X and Y depends on U and V. Okay, so this must be right, okay? Or you can also write it in this way, which means that U and V depends on X and Y. Right? And what we want to do is, I want to use the chain rule for F, and I want to talk about F as a function of U and V. Okay? And then think about X and Y as function of U and function of V. Okay, so, right, so F depends on U and U depends on X and Y. F depends on V and V depends on X and Y. So, and actually, if this is right, then if I want this, then I really want it to be in this way. Okay, so U is X and V is Y minus X. Okay. Then here is what we should be doing. If I want to know how F changes as you change X, then you have to asks the following. If you change the value of x ever so slightly, that's going to impact u and v, both of them, right? And when these values change, that's also going to change f. So see how the influences go up, right? So this is called the dependence diagram, just because it gives you how things are related. And there are two things that you have to consider if you want to know how f changes when you change x. One is that when you change x, it changes u, and then it changes f through u. So this route of influence is calculated in the following way. It's a change of f, measure how much u changes when, how much f changes when you change u, and multiply that by how much u changes when you change x. All right. That measures how f changes going through u. But that's not all, right? There's another route of influence. So what's the second term? Can you complete this for me? What should I put?
Parcel of f over the parcel of v times the parcel of v over parcel of x.
Yes, that's right. Okay. And the amazing thing about multivariable calculus, this is like one of the miracles of multivariable calculus, which is that you can calculate this separately, and then if you want to know the total rate of change, all you have to do is just add them. And at first it looks like a miracle, but then you realize that the reason it works is because all these derivatives are really trying to approximate a function by straight lines or planes. So when things are like straight, these things just work out that way. Okay? Some kind of a linearity that's in play here. All right, so now this is okay. Partial of f, partial u. That just has f and u. That's okay. What's not okay is partial u, partial x. I need to figure out what this is. What would this be? You're looking at how u changes when you change x, right? Well, what is u? U is x. So partial u, partial x would be what? 1. Just simply 1. Okay. Plus partial f, partial v is okay. But what is partial v, partial x? See, v is y minus x, right? So what? Minus 1, right? If you differentiate y minus x by x, y differentiated by x is 0, x differentiated by x is 1, but there's a minus, so it's going to be negative 1. So just as I said in the beginning that partial of f with respect to x is not the same thing as partial f partial u, although it seems to suggest that way, it's not the same. The actual answer is that partial of f with respect to x is partial of f with respect to u minus partial of f partial of v. Okay, now I think I gave you the crucial way to figure these out. So try to figure out partial f, partial y. How would you do it? Write down the chain rule and see if you can calculate some of the things that has x and y in there, and you end up with something. Who's done? Still calculating? Partial f partial y would be, again, the same thing as partial f partial u, partial y, partial f partial v partial y. Okay, what's u differentiated by y?
0.
0. What's v differentiated by y?
1.
1. Oh, that's interesting. This time, partial of f with respect to y is same as partial f with respect to v. Okay. And then, let's see, partial f partial x squared. Oh, this one's like taking partial derivative of a partial derivative. And we already know what this thing inside is. It's that one. So this is partial of f differentiated by u minus f differentiated by v. You know, there's several different notations in multivariable calculus, and they're all very convenient. You need to know all of them because people use them interchangeably, and often it becomes more convenient in one way than the other. When you have to write down the chain rule, this notation is the one that you want to use because it's more intuitive. But often you just want to write down partial with respect to u of f, just like that, for instead of this. It's easier to write, okay? And then minus partial with respect to v of f. And then once you do that, the resulting thing is again a function. I mean, if you compute this, that's again a function of u and v, or x and y. So when this is applied to this will act on this one exactly like this thing. Okay? So all I have to do is just try to follow the thing up there, and you write partial of u of. So I'm trying to use this formula again, pretending that this entire thing is f. Okay? So you have this, and then minus partial v, partial u f, minus partial v f. And then when this gets multiplied in, that's a second derivative, right? So that's going to be second derivative of f with respect to u minus second derivative of, well, it's differentiated by v and then differentiated by u, f. And this one is differentiated by u first and then v of f. But then second partials commute. So if you differentiate by u first and then v next, it's the same thing as differentiate by v first and then u next. So it's the same thing. So these two are exactly the same thing. So they can add together, okay? And then you have partial v with a minus this plus. So it's plus partial v squared of f. And now I just have to combine these two. So you get partial u squared f minus 2 partial u partial v of f plus partial v squared f. And that's it. Okay? So that's how you do change of variables for partial differentiation. Okay, since this is so important, let me put a question for you to try. Let me just write down the question. This time, let's say x equals to u plus 2v, okay, and y equals to u minus 2v. And question is find partial with respect to x in terms of uv, and also find second partial. Okay, so 1 and 2. Try this. Now, when I have a question on the board for you to try, I really want you to try it. I will be walking around to get questions, and I'll be also checking on you to make sure that you're doing your work. Yes?
I have this quick question.
Yes.
It seems like there's a gap in the knowledge. So, why does x, the changing of x, have relation with v?
Because x is so when you change x, it changes both u and v, right?
Oh,
If
yeah,
you alter the
because
value
it's-
of x, it will change the value of v and u at
It's
both
because
points.
this part of the equation.
Yes, yes.
Okay.
I understand. So that's a good question. So what's your name?
Terran?
Terran.
Terran.
Terran, okay. Terran, yeah, Terran. So I got a question, why changing x affects both u and v. And the answer is, if you look at u and v, they both have x's in there, right?
Mm-hmm.
So if you alter the x, it will change the value of u, and it will also change the value of v, because they both have x's in there. Actually, for this y, you can delete this line, right? Because u only depends on x, it doesn't depend on y. So in this case, the chain rule for f, with respect to y, only goes through here. So that's why this is 0. So it naturally worked out, but you could have just not written this and just wrote this to begin with, if you know that this is the dependence diagram. Okay, make sure you know this, because we are going to use this to solve a partial differential equation. People know what they're doing. You don't have anything to write with? Yeah. Okay. You should borrow paper. Oh, okay. Yeah. Mhm. Yes.
So, would the 2 be divided by here?
So one thing that you must do before doing this question is make sure that you can represent u and v as a function of x and y. So make sure that you can change this as u equals to something and v equals to something, and you should only have x and y in here. You can't have u and v on this other side. Okay? That seems to be something that some of you have trouble with. Make sure that you solve this for u and v. And then once you do that, you can easily write down the dependence diagram. Okay? Is anyone done? This one? You're done. Good. Just one person? Still working? You're done too.
I'm not sure of that.
Okay, good. But anyways, done is good. Are you done? Good. Good. Okay. Few people are done. Good. So let's try it together. If x equals to u plus 2v, solve for u. And then once you have that, you can plug that into the next equation. So y u equals 2v minus x, so you put it here. Oh, what's happening?
Yeah.
That's not right.
U is equal to x minus.
X minus 2v. Right, thank you. I got it backwards. So that's going to be y equals to x minus 4v. Move this to the other side, and then 4v equals to x minus y, and then divide by 4. Okay. If you think about what we're doing, it's like you have two unknowns, u and v, and think of x and y are the given. Okay. And how do you solve a system? You solve for one of the variables. So solve the first equation for one of the variables, and you plug into the next one. That's exactly what I did. And then since I'm trying to find u or v, and I only have v, so that's good. So I solved it for v, and that's it. Now once you have that, you can plug it back in here. And you get u equals to x minus twice of 1/4 is 1/2 x plus 1/2 y. So this right here, negative 2v is computed. And that gives you 1/2 x plus 1/2 y. Okay, so that's what we have. And then now we can talk about f as a function of u and v, and u and v as a function of x and y, like that.
I have a question.
Yes.
What does it do with the x?
Which x?
That
This one?
Yeah.
X minus 1/2 x is 1/2 x.
Okay.
Yeah. So you have $1, and you take $half away, you have still $half.
Okay.
Same thing. Yeah. Okay. So you have you write down the chain rule for f with respect to x. That's the same thing as asking how f changes when you change x, going through u and going through v. The one that's going through u is change of f with respect to u with respect to x, and then f with respect to v with respect to x. And then, let's see, what's u differentiate by x? U is this, right? So if you differentiate this by x, you get 1/2. So partial f partial u times 1/2 plus partial f partial v partial vx would be, what would that be? It's this one, right? 1/4. So that's the answer to the first one. Or you can rewrite it as 1/2 partial u f plus 1/4 partial v f. And if you accept that, then the second derivative with respect to x would be you're applying this twice to f. And actually this is somewhat dangerous. If you have any u and v in here, then you can't just simply square this as if it's an algebraic thing, because at some point you end up with the product rule and stuff like that. But if it's only constants, then you can just expand this like a polynomial. So it's going to be like 1/4 partial u squared plus this times 2, so it's 1/4 partial u partial v plus 1/16 partial v squared applied to f. So that's what the second one would be. So it would be 1/4 partial u squared f, 1/4 partial u partial v, f plus 1/16 partial v squared f. That's what it is. How many of you got right? Good, good. All right, nice. About half of you got it right. Good. Okay, we have two options. We can take a 10-minute break right now or just end 10 minutes early. Which one do you like? Vote. How many of you want to take a break right now? 2 people. 3. Okay. How many of you want to end 10 minutes early? Okay, 10 minutes early wins. All right. Sorry. You can just. Yeah. By the way, because I'm recording, if you're going out and in, just try to be quiet. Don't disturb. Am I recording? Make sure. Okay, good. All right. Okay, so now once we figured out how to handle the change of variables, we're already ready to solve our first partial differential equations. But let me first explain what partial differential equation is. Well, partial differential equation is a differential. It's an equation where you have partial derivatives in it. Very simple, right? If you have an equation with partial derivatives, that's partial differential equations. Now there are some physical applications that require partial differential equations. So a lot of the partial differential equations come with a name. And to give you some examples, you have like ut equals to k uxx, where this subscript means partial derivative. Okay, so this is u is a function of t and x, and you're taking the partial derivative with respect to t. You're taking second partial with respect to x, and k is some constant. This equation has the name heat equation. Another one is ut equals to c squared, actually utt equals to c squared uxx. And that one's called the wave equation. And then there's some crazy ones which we will never be handling here. Nonetheless, it's pretty important. So there's like ut equals to, I'm not so sure if I can write this correctly, gradient of u dotted with u. Right, I think it's a minus there, right? And then minus gradient of p plus some k times this one. Where u is a vector valued function. And this nabla here is a partial derivative with respect to x, I, partial with respect to y, j, partial with respect to z, k, and then this one is just nebula, dotted with nebula. This one has the name of Navier-Stokes equation. It's a differential equation. Many people try to solve. In fact, this one has a $1 million prize associated with it. You know that? You didn't know that? Okay, well, there's a Clay Institute. There's some place called Clay Institute, and they say that if you can show that this equation always has a solution, then you get $1 million. And you get a bunch of other prizes. And you get a job teaching at Harvard. It's pretty good. Yeah, well, it's really hard. We wouldn't even be able to start scratch this. I mean, we wouldn't even start doing anything on this one. This will be just too hard, outside the scope of this class. Okay. And there are many more. Okay. Now, I will eventually take a moment to explain why these equations work, what these differential equations actually do. But today I just want to solve one. Just if you solve one, you feel a sense of achievement. You feel like you've understood something. So I'm just going to solve one. Right? So I'm going to solve this one, this wave equation. And usually, these differential equations come with some additional boundary conditions and initial values and all that. I'm just going to assume that this is for all x from negative infinity to infinity, and for all time t beginning from 0. So I'm going to assume that utt equals to c squared uxx is true for all positive time and also for x from negative infinity to positive infinity. But the one that makes more sense is when you have x limited to, say, 0 to some length L. And in that case, this equation describes the equation of a vibrating string. And I'll explain later why that is so. Okay? But today we'll just solve one. All right. So how are we going to solve this? Well, first, I want to move this to this side and write down utt minus c squared uxx equal to 0. And then I look at this, and it looks like the following. It looks like second derivative minus c squared second derivative in x applied to u equal to 0. Yeah? And moreover, you can even think of this in a factored form. It's like partial t minus c partial x, partial t minus c partial plus c partial x, u equals to 0. And the reason this works is, as I explained, if you only have constants, then you can treat these like polynomials, and it still works. However, if you had some x or t here, then suddenly it doesn't work like that, because when you actually do the computation and you have some x's or t's here, when these things hit the other ones, you end up using product rule and so on and so it becomes really complicated. You can't use it like that. But if it's only constants, you can write it like this. Yes?
Can you remind me where the u equals 0 come from?
But that's not u equal to 0.
No, this is u equals to 0. Sorry, just a minute. So what I'm trying to say is that this is the original differential equation. I moved this to the left side, so you have equal to 0 on the right side.
Yes.
And then I'm rewriting this in operator form, where u is this function and you're applying this operator to u.
Oh, I see.
Now, the way you understand, and thank you for asking, the way you understand this is, it's like distribution law. So this times this means you take u and you differentiate twice in t, you get utt, right? And then when this hits this, this is differentiation by x and it's squared, that means you hit it twice. So you end up differentiating x in twice. And there's a negative c squared multiplied. So that's why this is exactly the same as that.
I see. Thank you.
Okay? Now, so this much is straightforward. What's not straightforward is why this is same as that. And in fact, this would be wrong if I had anything in front that has x or t in there. That would be wrong. Okay? Don't ever do that if you have x and t. However, these are all constants, so in that case, if you actually multiply this, apply this to this, and then apply this to this, you'll see that it's indeed same thing as this, and it behaves as if it's a polynomial. If you think of this as like t times cx times t plus cx, then if you actually multiply them like polynomials, you get exactly t squared minus cx squared, right? C squared x squared, right? Yeah. So because this is a difference, what is it called, dots formula, difference of two squares. You know that DOTS?
Long time ago.
Okay, long time ago, yeah, when you're doing algebra, right? So that's what you did there. But so actually, we didn't really have to do this one. Rather, this thing suggests the following change of variables. I want to say that u is equal to t minus cx, and v is equal to t plus cx. How's that? Right? Where c is a constant, x and t are the variables, and u and v are the new variables. And I want to do a change of variables for these partial derivatives. Okay. So I delete that. All right. Now we've done enough examples to know what we're supposed to do. You just add them up. U plus v is equals to 2t, so that t is equal to, wait a minute, I don't think I need that. Oh, this is good enough. All right, so I didn't have to solve for it at all. This is already in the form I want. Okay. So now let's try to do the following. If f is a function of, not f, sorry, u is a function of u, oh, I have u there. I'm using, oh, sorry. I can't use u and v because this has u, so I'll need to use something else. So p and q. All right, these are not the letters I like, but I guess I don't have a choice, right? Okay, so p is this and q is that, and then u will be a function of p and q, which will in turn be a function of t and x. And if I want u differentiated by t, this better be u differentiated by p times p differentiated by t plus u differentiated by q times p q differentiated by t. Agree? That's the chain rule, right? Mm-hmm. Yeah. And then up times, if you differentiate p by t, p is t minus cx, so what's p differentiated by t? What is it? What's p differentiated by t?
1.
1, very good. What's q differentiated by t?
1.
Again, 1, because q is t plus cx. If you differentiate t plus cx by t differentiated by t is 1, and cx, well, we're doing partial, so it doesn't have any t. That's considered as a constant, so it's 0, right? So you just get 1. Okay, and then what about ux? Let's try that. Now, again, this thing suggests that if you want to see how u changes with respect to x, you have to go like this and like that. So that's like up differentiation of p with respect to x, uq differentiate q with respect to x. No, what am I saying? Oh yeah, it is right there. Okay. What is this one?
Negative c.
P differentiated by x, what's that? Negative c, thank you. And this one? Positive c, right? And then now we're ready to do second partials. UTT is like applying t twice. But I already know what one derivative is. It's like up plus uq. And I also know that this one will behave exactly the same way. So that when this hits this, it'll be UPP. When this hits this, it'll be UQP. And then when this hits this, it'll be UPQ. But UPQ and UQP are the same thing. So when it comes to partial derivatives, the order doesn't matter, it's the same thing. Okay, and then when this hits this, it's UQQ. Oh wait, I messed up. I messed up, sorry. This wouldn't work. I actually need this to be CT, sorry, I messed up. It should be X minus CT, X plus CT. Okay, I'm sorry about that. So this one will have C in there. This one will have 1. Sorry, I got it backwards. So this will be negative C, and this will be positive C, and this will be 1. This will be 1. I'm recording this. It's not good. You have to do this separately. Okay. What else do I have? So what that means is this one will come with negative C plus UQ positive C. And so you have negative C partial P times C times partial Q applied to negative CUP plus CUQ. And then when this hits this, it's positive C squared UP, P. When this hits this, you already have a differentiation by Q, and you're differentiating again by P. So it will be minus C squared UQP. Okay, and then minus C squared UPQ, and then plus C squared UQQ. All right, I think that caused some confusion among you, so let me give you some time to do UXX then. So the way you do UXX would be, it's like this, right? But what is partial with respect to x? Partial with respect to x is like 1 times partial p, 1 times partial q. And this is being applied to u twice, right? Partial p plus partial q. Okay, so please try to expand this and see what you get. Yes?
I have a question.
Yes.
So, I forgot how you establish this result. I forgot about that.
Why I do this? Well, the thing is, I need this to be something simple, and I realize that.
You
Yeah.
expand it and you want to.
Yeah. So what I want is that if I do UTT minus UXX, I need a lot of terms to cancel. So the question is why I changed suddenly. The reason is I thought this should be T minus CX, but I was misled by doing this calculation. I really need the X to be just 1 and the other ones to be C, because only by that UTT will have C squared in them. I need the C squared here because there's already C squared here. So if you compute the UXX, you will see that there's no C squared there. So at the end of the day, when you multiply C squared and you subtract, you're going to see a lot of things cancel.
I see. Thank you.
Is that clear?
Yeah, that is clear.
Yeah. It's just so that somehow with this change of variables, this has become something easy. That's my goal. All right, just see what you get. If you're still lost, you can raise your hand. I'll help you out. Okay, you're okay. That's good. Yeah,
Okay.
came in late, so yeah.
So I have a question. So
Yes.
you know how you only put the BT
Uh-huh.
here, but you have the whole thing. So how did you make it put this in instead, not this?
Let's see. UX. Okay, here. Do you understand this result?
Yes.
Okay, because
Because the one.
yeah, it's here and then here, right? You want to know how U changes when you change X, but when you change X, it's going to affect F and Q, right?
P here.
Yeah, yeah. And then you want to measure how U changes going through P. That's change of U with respect to P times change of P with respect to X.
Okay.
That measures how U is being affected going through P. But that's not the only way that X affects U, right? It also affects going through Q. Oh, by the way, if you're done with that, make sure the next step is to calculate this, okay? Simplify this, okay? If you simplify, you're going to see something. All right. So that's why we get this. Is that fine?
Yeah.
Now, what this means is it's really saying that if you have U and you're differentiating by X, this is U differentiated by X, right?
Mhm.
It gives you U differentiated by P plus U differentiated by Q.
Okay.
Right.
That's how we did the one.
Right. So this in turn established that differentiating by X is the same thing as differentiating by P and differentiating by Q and adding them together.
Okay.
So if you just delete the U's and then look at what this operator is doing, that's exactly what it's doing.
Okay.
And then you write this twice, because it's done twice, right?
Okay.
Right, this and this. And then you just multiply just like how you multiply polynomials, except that every time this hits the other one, it's not multiplication, but it's derivative, right? So first of all, when this is hit, you have, when this is hitting this one, this is U differentiated by P, right?
Mm-hmm.
When this hits this, that's U differentiated by Q. Now let's see what happens if this hits this.
Same thing. UP.
This is already, yeah, two P's. You differentiate by P twice, right?
Mm-hmm.
And then when this hits here, what do you get? UQP, right? Okay, then this is U, PQ, UQQ. And these are, the second partial is commute, so these are the same thing. So you end up with UPP plus 2 UQP plus UQQ. Just like that. Okay? All right.
Professor,
Yes.
I just want to know how this leads to this.
Right. I think a lot of you are asking me the same question. So let me explain this again. So see, in multivariable calculus, notations are convenience, but also some source of confusion. And you need to be able to switch between notations easily. So when you have UT, UP, UQ, these are all partial derivatives, right? So what I want you to be able to do is, let me see where when you see this UT, when you see this UT, equals to negative CUP plus C times UQ, which is the result I got through the chain rule. You should be able to write this in this notation. And if you write like this, then you see that partial derivative of with respect to t is same thing as negative c partial p plus positive c partial q. It's like this. Differentiating by t is same thing as differentiating by p and q. multiplying by negative c and then adding it up. Okay? And once you accept that, then UTT, since this applied twice, you just have to apply this operator twice. That's all that's being done. Is that good? Right. Okay, so if P hits U, that's U differentiated by P, and if Q hits U, then U differentiated by Q. And then you still have to differentiate by P, differentiate by Q. P hitting UP, so it's UPP. P hitting Q, that's UPQ. UQP actually. This is already differentiated by Q, and then you have to differentiate by P afterwards. But the order really doesn't matter because partials commute. This is UPQ. When this hits this, that's UPQ. And when this hits this, that's UQQ. So you get UPP. These two are the same thing, so it's 2 UQP. QP plus UQQ. All right. So once you're done with that, I should. P equals to x. Did I put x minus e? Yeah. Okay. So once you're done with that, and you put it in here, then this would be c squared second partial squared minus 2 c squared partial t partial p. Oh, sorry, it's not t. P. PQ plus c squared partial q squared. So this much is partial t squared, right? Then minus c squared partial p squared plus 2 partial p partial q, and then plus partial q squared. All applied to u equal to 0. And sorry, I wish the ink was better. But if you look at this, you see that some terms are canceling, right? Which ones are canceling? Do you see which ones are canceling? No? You don't see which ones are canceling? Aren't these the same? With the minus sign, so they cancel? Yeah. What else?
Okay. What about -2 actually, never mind.
These don't cancel, they actually double, right?
Mm-hmm.
Yeah. What else?
And
The last one, these
Yeah.
cancel, right? Those cancel. So here's what we achieved. You have -4 c squared partial p partial q u equals to 0. So this equation in terms of p and q with these change of variables, this is what you get. All right, I mean, you might say that's still tough, but it's not. It's yeah.
you just forgot to write the u on the first half of the
No,
equation.
I was trying to say that all this is being applied
Oh, okay.
to you.
Okay.
Yeah. All right. Well, this is just a constant multiple, so I can just divide both sides by -4c squared. Oh, I should have given you a warning. But I thought you already knew. If you, most of you took calculus 4 or differential equations, ODE, right? And over there, you had to do crazy amount of calculation, didn't you? Right? Yeah. And this is PDE, which is like the next level. It's like even more calculations. So expect a lot of calculations in this class. Okay? And a lot of times, a math course is just in terms of your expectations. If you expect something easy and suddenly you come up with, you see something that's much harder than your expectations, then it becomes just too much for you, okay? But if you're already expecting something tough and you're seeing something tough, it's nothing out of ordinary. It's just, yeah, usual operations, okay? All right, so if you thought that all these calculations were crazy, that would be like the normal thing in this class. Okay, so now let's try to solve this. Well, now this is a lot easier to solve than the other one, because look at this. All you have to do is you integrate both sides by p. You integrate both sides by p. And that's going to get rid of the derivative, right? Because antiderivative cancels the derivative, so you just have partial with respect to q. Now, what do you get if you integrate 0?
Okay, so you integrate 0, you would get a variable back.
You get a constant?
A constant, that's my math.
Okay. Usually you get a constant, but this is partial integration.
Oh.
So if you integrate by partial integration, it's instead of partial derivative, it's a partial integration.
Even function?
Not that. You get a function of something. You get a function of, huh? P. Not P. Not P. You get a function of Q. Because look, if you took this equation and differentiated both sides by P, partial derivative, what happens to the right side if you differentiate by P? Does this have any P in there? No. So it's going to give you 0, right? So you do see that if you take this and differentiate by P, you get this. So the antiderivative of 0 is a function of Q. Well, you know, another way to think about it is, yes, indeed, it's true that if you integrate 0, you get a constant. But what is constant in this context? You're treating Q as a constant in terms of partial derivatives, right? So if you integrate and you get constant, those constants could be a function of Q. That's why you should put a function of Q here. All right? Okay. Next. What should I do next?
I have a quick question.
Yes.
So if you define partial derivative of P and partial derivative of Q as two factor, and then define their inner product as this kind of integration, and then if you get 0, that means they are orthogonal.
No. P and Q are not vectors at all. P and Q are some variables, just like x and y. So think of this. I want a function of P and Q, right? Where if you differentiate by P once and then differentiate by Q, you get 0. What am I? That's the question. Can you give me an example of such a function?
Right.
What function gives you a 0 if you differentiate by P and then Q?
P and then Q. It should be
Okay, that's a good question to think about. Give me a function of P and Q where you differentiate by P first and then Q, you get 0. Give me any function of P and Q.
PQ?
PQ wouldn't work. Let's try PQ. If you differentiate PQ by Q first, what do you get? You get P, right? And then you differentiate P, what do you get? 1, so it's not 0. Okay, so PQ doesn't work.
Just P?
Just P works. Okay, but let's be a little bit more non-trivial, okay? Something that has both P and Q. Yes?
P minus Q?
Yes, P minus Q would work.
Yeah, generally P plus CQ works.
Not only that, you can put squares.
Oh yeah, that's true.
Yeah. If you differentiate this by, so let's think about this one. If you differentiate by q first, what do you get?
Q first, negative.
Negative 2q, right? And then you differentiate by p, what do you get?
0.
You get 0. Okay, so that works, right? And the question now is simply, give me a function of p and q in general that would satisfy this. I think at this point you might even know the answer already, but let's just proceed, okay? So I differentiate, I integrate both sides by p, you get this, okay? Now what's the next step? What should I do if I want to do the next step? I integrate both sides by
Q.
q. Yeah, it's obvious answer. I think you guys are shy because it's the first class, okay? By the way, it's totally fine to come up with the wrong answer. That's actually, in math class, that's the only way you can understand it. When you try to write to say what you're thinking, and if it's wrong, then you get corrected. But if you don't say it, then you might end up taking the entire class with having the completely wrong idea of how things are going. And that will be very bad because once you're behind one class, then it's really hard to recover. Math classes are always following, yeah, it's cumulative. If you are behind one class, then that's devastating. So you don't want to do that. Okay? So make sure that if you have any questions, ask. And I'm already like way behind. I wanted to do a lot more today, but I'm only barely just doing this one topic. But it's okay. Like, if you ask more questions and we slow down and everyone understands, that's much better than nobody understanding anything, right? Okay. All right, so if you integrate f of q by q, well, we don't know what that is, right? But it's just some antiderivative of f. So usually they use a capital for antiderivative, right? So I'll just put capital F of q. But plus what? Not c.
P.
We're doing partial integration.
P.
So what? What? It's p, but what? Huh?
Never mind.
It would be plus c if this was a regular integral, right? But it's not. It's a partial integral. So what should we put?
CP?
Okay, see, I don't like that. CP is... Hey, what do you mean by CP? It's a constant that depends on p, right?
Yeah.
Well, how can a constant depend on p? But okay, so all I wanted was g of p. How's that? Okay. Some function of p, okay? Which is treated as a constant when you're doing antiderivative with respect to q. Right? Okay, all good? All right. Now, here's our conclusion. Q was x plus ct, right? And P was x minus ct, right?
Yeah.
And capital F is some arbitrary constant, and capital G is some arbitrary constant, okay? So I'm just going to call this one phi, and I'm going to call this one psi, and hopefully the Greek letters wouldn't freak you out too much. So I'm just going to call capital F as phi of Q is x plus ct. And instead of g, I'm going to call it as psi of x minus ct. Okay. So that's the solution. Oh, by the way, at this point, you should kind of see why this is the general solution to this. If you have a function of q plus function of p added together in this format, if that's the shape of u, of course, when you take this and differentiate by p and then q, or differentiate by q and then p, it will always give you 0. Don't you think? Right? Yeah. So when you get the answer, try to see why this makes sense for this. Makes sense? Okay. That's good. Okay. All right. Okay. All right. So we have the answer to this question. Answer to this question would be u equals to phi x plus ct plus psi x minus ct. Where phi and psi are arbitrary functions. Okay. Now, let me go one step further, and we will try to come up with the initial value problem. So in ordinary differential equations, if you had something like u double prime plus u equals to 0, how many initial conditions were you supposed to provide? You give u of 0 equals to, say, 3, and you have to do u prime of 0 equals to some other value, right? If you do this, then you can solve this uniquely, right? You get a unique solution. Do you agree? Hopefully you didn't forget this, because it would be very bad if you forgot the ordinary one. All right. But all I'm trying to say is that if it's the second derivative, second order, then you provide two initial conditions. Okay. Now here, the wave equation is a second order differential equation in terms of t, and at time t equals to 0, that's when you have the initial condition, and because it's the second order, you can provide u of 0 and also u prime of 0. Okay, so let's ask question 2. So we already solved one question. Now I'm going to turn this into a initial value problem, and here's what I'm going to do. I have utt equals to c squared uxx, and u is a function of x and t, and then ux0, so that's like t equals to 0, okay, is given as some function x. And then ut x0 is given as function g of x. And this makes sense because if you have u of xt, it's a function of x and t, but if you plug in a value for t, then t goes away. You get numbers replace the t, and you end up with a function of x. So that's why this makes sense. Okay, the initial value will be a function of x. Same thing here. You differentiate uxt by t once, and then you plug in t equals to 0. Again, that will make all the t's disappear, and you end up with a function of x. Okay, so that's one thing. And then I want to solve this. Okay. So find uxt. And I forgot to say that this is true again for this. Okay. So I should write it somewhere. T greater than 0, and then x is between negative infinity until positive infinity. Okay. So let's try to solve it. And now it's a lot easier because we already know the solution to the first one. So we start from this. We're not starting from scratch. We start from this solution. So we already know that uxt is some function of x plus ct plus another function of x minus ct. Okay. And then guess what we want to do? What should we do from here? What's the only thing you can do?
Differentiate
By what?
t.
T. Yeah, you differentiate by t. What would you get if you differentiate this by t?
C.
C phi prime of x plus ct, right?
Okay.
Okay. Plus, what about this one?
Would it be negative C?
Negative c, perfect. Right? Phi psi prime x minus ct, just by the chain rule, right?
Oh, so
Yes.
you're treating one of those as constants, like x.
Yeah, I mean, this really means partial derivative with respect to t. So you're treating x as a constant when you differentiate. C is already a constant, but because we're doing partial derivatives, x is a constant as well. So you're really looking at this as a function of t. And how do you differentiate this as a function of t? You have to use chain rule, right? So you differentiate the outside function, right? And you pull the inside out, you differentiate the inside function, which gives you c. Right? Same thing here. Okay, good. All right. Now what? What next? You know, everything will follow. I mean, there's like only a few things you can do. What should we do next?
Plug in
Plug in what?
0.
0 into t, right? So we have ux0 equals to psi of, tell me what you get.
Psi of x.
X, right?
Phi of
Plus psi, and the phi of x and psi of x. Okay. And then u t of x0 would be
C phi
c
prime.
phi prime of x plus, actually minus, c psi prime of x. And this has to equal to, the first one has to equal to
Fx. Oh, wait.
fx, right, yeah, I got confused. Sorry. The second one has to equal to
Gx.
gx. Good. All right. This will be very easy if this was phi and psi, but there's a prime, right? So we will have to integrate both sides. Okay, so we'll integrate. Take this second one and integrate by x, and you get c times psi of phi of x minus c times psi of x equal to integral of g of x dx. Is that good? Okay. And then we take this f, but I want to cancel something, so I'm going to multiply c to this one. So c times phi of x minus plus c times psi of x equals to c times f of x. And then we add them together so that you get 2c phi of x, this one will cancel, equal to c f of x plus integral of g of x dx. And we're almost there. See, now we can solve for phi of x by dividing by 2c. So you have phi of x equal to c over 2c will be 1/2, right? It will be 1 over 2c of integral of g of x dx. Okay. How can we get psi? Now, 2 ways. You can plug this into here and solve it.
You can just subtract it.
Yeah, you can use as subtract, right? So that'll be another method. So subtract. Then this will cancel and you end up with negative 2c of psi of x equals to negative c f of x plus integral of g of x. And this time if you divide by negative 2c, you get psi equals to 1 over 2 f of x minus 1 over 2c g of x dx. Well, since we figured out what psi and x is, that allows us to now reconstruct u and x and t, u of x and t. So let's see. However, there's a problem here. See, psi of x is this. Now all it remains is we just have to replace x by x plus ct. See, instead of this x here, if I plug in x plus ct, we're done. Right? And I plug into this one as x minus ct, then we're done. Right? Then we know what uxt is. However, the problem is, if you try to plug in here, then that causes a problem because you can't integrate by x plus ct, so that causes a problem. So instead of doing it like this, we want to write this as a definite integral. So what's another letter? I don't want to use t. Let's use can't make up my mind for a good letter. Should I use y? That doesn't make sense either. I wonder what the textbook says. I think I did see in some cases they use x prime, but that's ugly. It's confusing with the primes. I'll just use y. How's that? Is that okay? Y? Right. So I'll just use y. But then this will be a function of y. So instead I'm going to write this as a definite integral. So I'm going to put 0 to x. 0 to x. Okay. So that this one also becomes 0 to x. Is that okay? Yeah. I mean, if you integrate and you plug in x and 0, of course, it will be a function of x, right? So it's the same thing as before. Whether you have this or this, well, this is actually less ambiguous because if you integrate like that, then you have a constant c, which is not determined, which is not good. But if you write like this, that's okay. Right? So let's write it like this, and the reason I like this is because now it's easy to plug in x plus ct or x minus ct here. That's not a problem. Before, plugging in here, that's going to cause a problem because you have to change this as well, and it doesn't make sense. Okay. All right. So with that, here is what I have for phi of x plus ct, which is 1/2 f of x plus ct plus 1 over 2c of integrate from 0 to x plus ct of g of y dy. And then psi of x minus ct, all I have to do is just take that, replace x by x minus ct, so you have 1/2 of f of x minus ct plus 1 over 2c, 0 to x minus ct, g of y dy. And then, what's happening now? Yeah, so now I have to add them together, right? Oh, this one is a minus, sorry. This one is a minus. So here's some additional tricks I'm going to do. I'm going to change this as a plus by switching these two around. You know that trick? You can switch the boundaries upside down and you put a plus.
Yeah.
So I'm going to put plus here and then I'm going to put 0 here, x minus ct here. Okay, and then if I add them together, this is by definition our uxt, right? So we have uxt equals to 1/2 f of x plus ct plus f of x minus ct plus 1/2c, and then the reason I flipped them around is because then this integral is from here to 0 and then 0 to there. So that can be added as a single integral, right? And that integral becomes what goes here and there. Here, what goes in there?
So negative x minus ct.
X minus ct, and then what here?
X minus ct.
No.
Oh.
It's from this to 0 and then 0 to here, so it's from x minus
plus
ct,
ct.
x plus ct, yes. Right. And then g of y dy. Okay, so that's the general solution for two initial conditions. Okay. Yes.
Can you explain again why you introduced gy?
Oh, so if you saw what I did, I had to plug in x plus ct, right? But can you plug in x plus ct here? I mean, does this notation work? Integration of x plus ct dx plus ct, does that look natural to you?
No.
It doesn't make sense, right? So it's hard to understand what's going on if you write like this. So that's not a good way. So instead, you write it as this thing. It's like this. Instead of, so you can have integral of 2x dx. That's going to be x squared, right?
Yeah.
But with plus c. But you can also rewrite this as integral of 2y dy, 0 to x. What would this give you? Y squared, and you plug in x and 0, so this is going to be x squared, right? Without the plus c.
I see.
Yeah, so that makes it easier because we don't have the c. It's a definite answer, rather than something ambiguous.
Okay.
That's why this is more desired than this one. Okay.
Another reason, is it because t is from 0 to infinity to it's always greater than 0? That's why you.
No, that has nothing to do with that. No, it has nothing to do with that. Okay. So this is what you have, and this equation actually gives you some more insights into the wave equation. So first of all, there's a name for this answer. It's called D'Alembert solution. Called D'Alembert solution. And usually we teach this like somewhere in the middle of the semester, but I thought that this is easy enough that we can solve in the first class and then also do a couple of more stuff. I was too ambitious for the first class. So right. Okay, I'll have to try to see how the pace for this class. But anyways, let's go D'Alembert solution. And this one has an interesting thing to say about the wave equation. It's like this. See, you can think of u as a function of t and x, actually x and t, and the value of u can be like the z-axis, right? So like you have some initial data here, right? And then it will carry over to the next one and next one and so on and so on, right? So you have something here, and then next and next, and what happens is the speed of the information is constant. So in other words, if you have some data over in the initial position, and the value of f at this position, because it's carrying over as x plus ct and x minus ct, it goes in two directions. If x minus ct is constant, that's going to be, yeah, so if x minus ct is a constant value, so some constant, then that's t equals to 1 over c x plus c minus e over c. So it's a positive slope of 1 over c. So this is actually a positive slope, and this x plus ct will be a negative slope. So the information of f at a point will spread like this and this. Another way to see it is that at any point in space, this data will be coming from here and there. So x minus ct and x plus ct. So the value of f here and there will be added up to give you the value here. And for the g, every information between x minus ct to x plus ct would be sent over here. That's how it works. And therefore, these lines here, these are called characteristic lines. And secretly, what's happening is that we're really doing special relativity here, because c is like the speed of light, and information is traveling at the speed of c. The actual equation for special relativity of Einstein is actually that form. Okay. So that's another thing. And then in a general perspective, completely apart from the wave equation, in a purely general perspective, this solution teaches us three things about this wave equation. What are the three things we can learn about the wave equation here? So, lessons we learn about wave equation. And it works like this. You have first, if initial value, so u and ut are given at t equals to 0, uxt is unique. There's only one solution for it, right? You have a unique solution. So this is uniqueness. Secondly, if these are given, solution always exists. Okay, so that's existence. And third, if fg, the initial data, is slightly changed, so if these functions are changed slightly, then because u is also depending on these, u would also only change slightly, right? So u changes slightly. Now, the way that I'm speaking about item 3 is very crude. It's there are better ways to say this, but for that you have to talk about norms of function, and it's a lot more involved. But this one is about stability. And if a differential equation has all three properties given, we say that the differential equation is well-posed. We say a differential equation is well-posed if uniqueness, existence, and stability holds. Okay? If all these three are true, then we say it's well-posed. And we just, by solving it, we actually showed that the solution is unique, solution exists, and the stability is true. Now, if you have solved some ordinary differential equations, that's another thing. I think sometimes people teach differential equations, and they talk about. Have you heard about this in ordinary differential equations? You haven't. Oh, that's terrible. These are very important concepts when you solve differential equations, and not because they help you explicitly, but because this is like the underlying assumption whenever we solve differential equations. So this is what you're going to find in any differential equations. Often, today we honestly solve this equation, right? I can say we honestly start from scratch and we did everything, we solved it, right? But often what we're going to do is we're just going to look at something and say, hey, let's see if we can solve it this way. And if it works, hey, we made it, and it works, okay? And without really solving it, we'll just make guesses, and it's just like, when you had y double prime plus 3y prime plus 2y equal to 0, how do you solve this? You write down characteristic equation, right? R squared plus 3r plus 2. Now, why does this work? Did anyone explain why this works? See, that's the problem. People just solve without thinking about why this works. It's really like this. What's really being done is you say that I think solutions like this form would work, right? And then you plug it in and it says, oh, it works, right? And then if it does work, then you take linear combinations and you check and it still works. And then at some point you say, oh, I think I find all the solutions. And that totally doesn't sound like math. Does it sound like math? That's like what physicists would do. They would just manipulate terms and plug it in. If it works, that's good. That's the way that physicists do. But often in a differential equations class, you're going to see that that's what we do. We just make things, plug it in, works, great. But it's still math. And the reason it's still math is that these are already proven for us. So for differential equations, uniqueness, existence is proved. So what it means is that if we come up with any kind of ansatz, if it works, we know because the answer is unique, we found that unique solution. That's how this logic works. There is a logic, but the logic is only complete if there is a uniqueness and existence. Okay? And that's a big thing that people don't really explain very well. From now on, we are going to assume that a lot of these equations that we solve will have these properties, although I might try to prove a few of them, but it's hard. Okay? But if you assume that this is done by some really heavyweight mathematicians, then you can gladly use their result and say, okay, from now on we'll just make guesses, and if it works because we already have this. Okay? So that's the wonderful thing about these well-posedness, right? Okay, that's all for today. Thank you.